guys, welcome back to Octet Academy. In the last few weeks, we've learned about atoms, compounds, elements, mixtures. We've learned about the various atomic models and the subatomic particles that we have. We now know that atoms are made up of electrons that are negatively charged, protons that are positively charged, and neutrons that are neutral. Today, we're going to be learning something else that is going to build on what we've learned so far. We're going to be learning about atomic number, what an atomic number is and how it is calculated. We're going to be learning about mass number and how you can calculate that as well, and the relationship between atomic number and mass number. We're also going to be learning about relative atomic mass, relative molecular mass, and finally we're going to learn about moles, what moles are and their importance in chemistry, and also how we use moles, how we use the number of moles of a compound or of a material to calculate other things like percentage composition and volume of a gas. So let's get right into it. We've previously learned that atoms have subatomic particles such as protons, electrons, and neutrons. And we've also learned that the proton and the neutron are the center of the atom in the nucleus, while the electrons revolve around the nucleus. Now, what is an atomic number of an atom or an element? The atomic number of an atom is the number of protons in that atom, and it defines that atom or element. Most times, when the atom is neutral, the number of protons is usually equal to the number of electrons at its natural state when it is neutral. So let's take carbon for example. Atomic number is usually represented by Z, like we have seen here. Atomic number is usually represented by Z. And let's take carbon for example. Carbon has 6 protons. So in the nucleus of carbon, we're going to have 6 protons. 5, 6. And then you have neutrons as well. Neutrons are neutral. And then we're going to have electrons revolving around the nucleus. For carbon, there are 6 electrons as well. So we're going to have 2 in the innermost shell, and we're going to have 4 electrons in the outer shell. So for carbon, the number of proton is the atomic number. So the atomic number of carbon is equals to 6, because that is the number of proton. So for every atom and every element that you might come across, the atomic number is the number of proton. Why the mass number is equals to the number of proton plus the number of neutron. So if you see a periodic table and say that, oh, the mass number of carbon is 12, this is how we arrive at that answer. So mass number of carbon is equals to 6, the number of proton, plus 6, the number of neutrons, which gives us 12. So just to recap, atomic number is equals to number of protons, and mass number is equals to number of protons plus number of neutrons. So that means if you know the atomic number, you can find the number of neutrons. If you know the number of neutrons and the number of protons, you can find the atomic number by using this formula. I hope you understand it now. Let's move on to the next one. We've previously learned that atoms have subatomic particles such as protons, electrons, and neutrons. And we've also learned that now we've learned that atomic number is the number of proton in an atom, and that mass number is the number of proton plus the number of neutron that you have in an element. These two parameters, atomic number in particular, the number of proton or the number of electron in a neutral element, is used to arrange all elements in the periodic table. The periodic table is the table that contains the list of all known elements, both naturally occurring and man-made elements, are arranged in the periodic table using atomic number, that is the number of proton in each element. So if you look at any periodic table, it's going to contain information about all element, and each element has a specific placement on or in the periodic table. It's going to contain the symbol of that element, going to contain the name, and then you're going to have the atomic number at the top, and then the mass number. You're going to find all of that for all known elements in the periodic table. I'm going to leave a copy of the periodic table PDF in the comment section or in the description box for you, so you can download that for your personal use. Another concept that has come up from atomic number is the relative atomic mass. That is, as the name implies, the relative atomic mass is the average mass of an element compared to 1/12 of the mass of a carbon 12 atom. And you might wonder, why is that so? This is to allow for comparison of the masses of various elements, and to bring about a kind of unification in terms of measuring their masses. So their masses are compared to that of 1/12 of carbon 12. And it has no unit. This is a unitless parameter, and you can find this on the periodic table as well. So for example, the oxygen atom here, so 8 is the atomic number. That tells you that's the number of proton in an oxygen atom. This is the symbol, and the relative atomic mass is 18, and then you have the full name of the element. So you have the relative atomic mass of every element next to the chemical symbol of the element on the periodic table. So for oxygen, it is 16. When atoms combine together, we've learned that in the past, that they combine together to form molecules with themselves or with other atoms. So when we have a molecule, another parameter that relates to a molecule is the relative molecular mass. And the relative molecular mass is very simple. It is just the sum of the relative atomic masses of all the atoms in that molecule. So let's take an example. The relative molecular mass is gotten by adding together all the relative atomic masses. Let's take carbon dioxide, for example. So example, CO2. That's carbon dioxide. What will be the relative molecular mass? Bear in mind, the relative atomic mass, represented as RAM, of carbon is 12. Relative atomic mass of oxygen is 16, like we saw in the previous slide. So what is the relative molecular mass of CO2? The relative molecular mass of CO2 would just be the sum of the relative atomic mass of the atoms that make up the molecule. So here we have CO2, one carbon and two oxygen. The relative atomic mass would just be the relative molecular mass will be the relative atomic mass of carbon plus the relative atomic mass of oxygen. But we have two oxygen, so it's going to be times 2 because we have two atoms of oxygen. So that is going to be 12 plus 16 times 2, and that will be 12 plus 1, 32, and that is going to be what? 44. The relative molecular mass of CO2 is 44. When atoms combine together, we've learned that in the past, that they combine together to form molecules with themselves. Or let's take another example. What is the relative molecular mass of H2SO4? That is what we're going to be looking for. The relative atomic mass of hydrogen is what? is 1. The relative atomic mass of sulfur is 32, and the relative atomic mass of oxygen is 16. Bear in mind we have 2 atoms of hydrogen, 1 atom of sulfur, and 4 atoms of oxygen. So relative molecular mass of H2SO4 will be equal to 1 times 2 to represent that of hydrogen, H2, plus S is 32, plus oxygen, we have 4 of such, 16 times 4, 04. So that is going to be 2 plus 32 plus 64, and that will be 98. So the relative molecular mass of H2SO4 is 98. I hope you understand it now. Good. Let's take another example. What is the relative molecular mass? Slide 7 going in 3, 2, 1, 0. So what are moles? A mole is a unit of measure in chemistry, and it is number of particles in a particular substance. So the number of particles you have in whether an element, an atom, or a molecule refers to 1 mole of that substance. And this number is approximately the Avogadro's number, that is 6.022 times 10 raised to the power of 23. So 1 mole of an element will contain 6.022 times 10 raised to power 23 particles. 1 molecule will have that number of particles. Ions, 1 mole of a particular ion will have Avogadro's number of particles in there. So numerically, how do we do this? So we've said, numerically, how do we do this? Mole contains or is equal to 6.022 times 10 raised to power 23 particles. So whether it is an element, an atom, or ion, this is the number of particles that it will contain. How do we work with this numerically in chemistry? Numerically, number of moles, it is represented as N. So anywhere you see small letter n, that is telling you the number of moles of a particular substance is equal to the mass of the material divided by the molar mass. Remember, we've just learned how to calculate the molar mass. So if you know the mass of a material and you calculate the molecular mass like we just did using the atomic masses of the atoms that make it up, then you can find the number of mole. Like every scientific concept, unit is very, very important. If you write a numerical value, do any calculation without the appropriate unit, that is not correct. What is the unit of moles? It is the unit of mole is mole. So we write as 1 mole. So if I want to write X contains 2 moles, right? 2 mole. Okay? Mole contains or is equal, number of moles is mass divided by the molar mass, and we've also learned how to calculate the molar mass of different molecules. Now let's take this as an example. We've been given the mass of carbon dioxide as 88 grams. So from this question, the molecule we're working with is CO2. Mass of CO2 is 88 grams. We've been asked to calculate the number of moles. Calculate the number of moles. That is what we don't know. And we know that number of moles represented as N, is equals to mass over molar mass. We've already been given the mass. Let's calculate the molar mass of CO2 again. CO2 is carbon and oxygen. Carbon is 12, and we have two atoms of oxygen, so 16 times 2, that is 12 plus 32, which is equal to 44 grams per mole. It is important to put the right unit. So here we have 1 mole of CO2, and that tells us that the molar mass is 44 grams in 1 mole. So now let's find the number of moles that we have in 88 grams. Yes, so let's plug this value in here and use this as the mass. So again, going back to our formula, number of moles N will be equals to the mass that we've been given, 88, divided by the molar mass, 44. And then that would be what? 2 moles. So the number of moles, so we can conclude that 88 grams of CO2 contains 2 moles of CO2. Number of moles is mass divided by the molar mass. Let's take another example. We want to calculate the number of moles in 18 grams of water. So the mass that we've been given to work with of water is 18 grams. Number of moles we do not know. That's what we've been asked to calculate. So we remember number of moles N is equals to mass over molar mass, right? So we've been given the mass. Let's calculate the molar mass of water. Molar mass of water H, hydrogen is 1, oxygen is 16. We have we have 2 hydrogen, so that's going to be 1 times 2 plus 16 because we have 1 atom of oxygen. So that's going to be 2 plus 16, and that's going to be 18 grams per mole. That is, in 1 mole of water, you have 18 grams. Now let's go back to calculate the number of moles. Number of moles is equal to mass over molar mass, like we know. And in that case, the mass we've been given to work with here is 18, and the molar mass is 18 as well. So that means in 18 grams of water, there is 1 mole of water. And with this formula, if you know the number of moles, you can calculate the molar mass. You can use that to find the mass. The same way, if you don't know the molar mass, you can use the number of moles and the mass to calculate the molar mass. Let's take another example. So why do we bother calculating number of moles of a material? One, knowing the number of moles tells us the combining ratio. So with the number of moles, we can tell when 2 molecules or compounds react together, we can determine in what ratio they combine together using our understanding of moles and how they relate to, say, mass and molar mass. So they help us to determine the amount of a substance, and we can connect that to the number of particles. So now we know that in 18 grams of water, there is 1 mole. And if you don't know the molar mass of a material, if you know the number of moles, that is the number of particles, you can use that to work back. If you know the mass and the number of particles, invariably the number of moles, you can use that to determine the molar mass as well. Another thing that we can do, that we can use our understanding of moles and the attending calculations to do, is to determine the percentage composition. That is, how much of X is in a particular compound. You can do that using a few simple steps. It shows us the percentage of each element in, say, a compound. So if you have a compound like H2SO4 that has three different atoms, three different elements making it up, you can determine the percentage composition of each element in these types of compound that have more than one element that make them up. So any compound that contains more than one element, you can use our understanding of moles and that attending calculation to calculate the percentage composition. That is how much does each component in terms of different atom contribute to the total compound. And there are four easy steps you will need to follow. The first thing we'll do is find the molar mass of a compound. We've learned how to do that. Then we'll find the total mass of the elements that you are interested in. How much of that element do you have? Divide the element's total mass by the molar mass and multiply it by 100 to get the percentage. Let's take an example of that. It's very, very easy. Now, we all know water is H2O, right? We know that by now. This question wants us to calculate the percentage composition of hydrogen and oxygen in water. So this is an example of a compound that has more than one atom. Hydrogen is a different atom, oxygen is a different atom. But we want to determine what is the percentage contribution of each atom. Now, atomic masses we've been given, hydrogen is 1.0, oxygen is 16.0. Those are the atomic masses. And like we stated earlier, when you want to calculate the percentage composition, first you find the molar mass of the compound. So let's find the molar mass of water. It's going to be, you have two hydrogen, 1 times 2 plus 16, and that is going to be 18 grams per mole. That is, in 1 mole of water, this is the mass per mole. 1 mole of water has 18 grams of that material in there. Let's find the total element or total mass of the elements that we are interested in. What is the total element that we are interested in? It is 2, right? Because we are interested in hydrogen. So percentage composition of hydrogen, we have 2 hydrogen in there, right? Will be equals to 2 times 1.0 because you have 2 hydrogen divided by the molar mass that we've calculated, 18, times, because it's in percentage, 100. That should give us something like 2 divided by 18 times 100. That should come to around 11.11%. So the percentage of hydrogen in 1 mole of water, don't forget that is important because we're dealing with just 1 mole of H2O, is 11.11%. Now let's find the percentage composition of oxygen. Percentage composition of oxygen. We do the same thing like we did for hydrogen. Here we have just 1 oxygen and that is 16, right? So we have 16 divided by, what is the total? 18 times 100. And that gives us something around 88.89%. If we add these two together, you get 100, and we've been able to determine the percentage composition of the atoms that make up water. Let's take another example. Now, let's take another example with percentage composition. Determine the percentage by mass of sodium in sodium chloride. That's table salt. Sodium is 23.0 and chlorine is 35.5. Again, the process is the same. Let's find the molar mass. Molar mass of sodium chloride. We have 1 of each atom. That will be 23 plus 35.5, and that is going to be what? 58 0.5 grams per mole. Remember, we're working with just 1 mole. Important to always add the unit. So molar mass is mass per mole. Okay, we've gotten the molar mass. Sodium is 23. So what is the percentage of sodium by mass? 23 divided by 58.5 times 100. And that is going to give us something like 39.32%. That is percentage of sodium by mass in sodium chloride is 39.32%. Like I stated earlier, one of the most important uses of the concept of mole in chemistry is that it helps us to determine the combining ratios in reactions and when we form new materials through chemical reaction. For example, look at what we have on this slide. Using moles in equation, from this equation we can get the mole ratio. So we have a reaction between calcium carbonate and hydrochloric acid, and we can see here that only 1 mole of calcium carbonate reacts with 2 moles of HCl, hydrochloric acid. So in this case, if you want to do this reaction, you know that you need 2 mole equivalent of HCl for a complete reaction to occur. So that is one of the application of the concept of mole. It helps us to determine the combining ratios and how to optimize forming new materials through chemical reaction. And you can see that even though we start with 1 mole of calcium carbonate and 2 moles of hydrochloric acid, we have formed 1 mole of calcium chloride, 1 mole of carbon dioxide, and 1 mole of water. So again, that shows us the mole ratio of the reactant and the product. Another example is the formation of ammonia that is done with the reaction between nitrogen and hydrogen. 1 mole, we only need 1 mole of nitrogen gas and 3 moles of hydrogen to give us 2 moles of ammonia. Another parameter that we can deduce from our understanding of mole and mole concept in chemistry is the volume of a given gas at STP. This is an important distinction. This only applies when the gas is at STP, that is standard temperature and pressure. So at standard temperature and pressure at STP, 1 mole, that's very important, of any given gas occupies 22.4 dm cube of volume. So the volume of any given gas, the volume of 1 mole of any given gas at STP is 22.4 dm cube. So what that tells us is that if a gas is at STP, standard temperature and pressure, 1 mole of that gas, regardless of the type of gas it is going to occupy, the volume is going to be 22.4. And we can use that also to calculate the volume of a gas that is given off in a reaction that is done at STP. We can use the volume given off at STP to calculate the number of moles and the number of particles that is in a given in a particular gas. Let's take this as an example. We are asked to find the number of moles. That is, what is the number of moles? Number of moles, N, don't forget, in 0. What is number of mole in 44 point in 44.8 dm cube of a gas at STP? Again, this is an important distinction. It is only when it is stated that it is at STP that we can use this formula. And we know that 1 mole of any gas, of a gas at STP, occupies 22.4 dm cube of volume. So what will be the number of moles? We don't know, in 44.8 dm cube. If we cross multiply, so we have 22.4 and the unknown number of moles times, which is equals to 44 times 1, which is still going to be 44.8. So x is equals to 44.8 divided by 22.4. Bear in mind, we're calculating for number of moles. So x is equals to what? 2 moles. So that is 44.8 dm cube of a gas at STP contains 2 moles. So if we know the volume, if we know that every gas occupies 22.4 dm cube at STP, we can use that to calculate the number of moles of that particular gas. So we have some practice questions for you again. The first one is that state the mass, what is the mass of 3 moles of oxygen? 1 mole of oxygen is O2. So 3 moles of oxygen would be, you have 3 O2, and you know oxygen is 16, so that is going to be 3 times 2 times 16, and that is going to be what? 96 grams. That will be the mass of 3 moles. You should be able to do that by now. Now, another interesting question we have for you, we're going to solve this together, will be what will be the number of atoms present in 5 grams of sodium? We've said 1 mole of a material, 1 mole of an atom of a compound will contain 6.02 times 10 to the power of 23 particles. So they're asking us that how many particles do we have in 5 grams? We know that 1 mole contains 6.022 times 10 to the power of 23 particles, right? So how many particles are there in 5 grams? Let's convert the gram to the mole, right? They've given us that sodium is 23. That is, 1 mole of sodium is 23 grams per mole, right? So we have 5 grams. How many moles do we have in 5 grams? That's what the first thing we need to find, because we need to find the number of moles in 5 grams, so we can then use that to calculate the number of particles, because when we know the number of moles, we can plug that in here. Number of moles, remember, is mass over molar mass. And we've been given a mass of 5 grams. Molar mass of sodium is 23. So number of moles here will be equal to 5 divided by 23, which is equal to 0.217 moles. So that is the number of mole in 5 grams. So 5 grams of sodium is equal to 0.217 moles. Okay, but we know that 1 mole of sodium or of any material is equal to 6.022 times 10 raised to power 23 particles. So how many atoms do we have in 0.271 moles? So we just plug that in here. We don't know that yet. So if we cross multiply, the number of moles, the number of particles rather, will be equals to 0.217 times 6.022 times 10 to the power of 23, and the number of particles will be 1.3 times 10 raised to power 23. Don't forget, this is a unitless parameter. It's a unitless parameter. So number of atoms or particles in 5.0 gram of sodium is equals to 1.3 times 10 raised to power 23. So we have some practice questions for you again. And that's it, guys. We've come to the end of today's lesson. I hope you've learned one or two things. At the end of this lesson, you would have learned how to calculate atomic number and what they are, mass number, relative atomic mass, relative molecular mass, molar mass, the number of moles, and how you can use your understanding of the number of moles. If you know the number of moles of a material, you can use that to calculate percentage composition and the volume of a gas at STP. Don't forget to like, follow, share, and subscribe. Share with your friends. If you have any questions about this topic or any chemistry topic, leave it in the comment section and I'll be happy to answer your questions. See you next time. Bye bye.